everybody that used LLMs extensively encountered hallucinations, which is the term used to describe being wrong with confidence. Some of the methods I'll show you today will address that. The other is poor multi-step reasoning, which is when you have a task with multiple steps, you need a high degree of reliability of each one of the individual steps in order to have overall reliability. And current LLMs are not good at such tasks. So let's talk about the agenda. So we'll talk about all this stuff. So it's not going to be deep, like we're not going to go deeply into each one. We have sessions for a lot of the things here, but just to get the terminology, to familiarize you with what's out there, what's coming, we thought it will be a good idea. So another thing that's to keep in mind that everything I'm going to talk today, like to tell you today, is assuming that the prompt quality is to the maximum, because it's really the single most important thing that you can do. But after you finished with your prompt, you have a lot of other tools. And the other is some of the things I'm going to talk about today are not going to be relevant maybe in next year, because this field is moving really, really fast. Some of the things that are external tools or external methods like RAG or some of the agentic interfaces are going to be probably abstracted away in next level of frontier models. But anyway, some of the methods will maybe be more relevant. So anyway, it's good to know them for now, if you want to build something that is reliable on top of LLMs. So we'll start with RAG. Who didn't heard about RAG? Good. Okay. So I'm not okay. So RAG is a retrieval augmented generation, which is the fancy name for just memory, just external memory. Basically, it's a way to inject knowledge to post-training. Basically, what you have is you have some data that the LLM doesn't know about or knows poorly, and you want the LLM to know about this data. So you have some options. One option is RAG. What you can do is basically like the overviews of RAG is you can take your data, separate the data into chunks of text, and do some operation that will touch upon vectorization or embedding. And then when you have user query, you can retrieve stuff from your storage vector database, take out the chunk that corresponds to the vector, and then append that chunk in the context so that the LLM will have your piece of information or knowledge in the context. So, okay, let's break that apart. I'm not going to go into how this is made, but we have options. You can easily today get a text chunk like this, like in version 2.3.1 of the product, blah, blah, blah. You can pass it through some kind of embedding model, which you have a leaderboard of the best. Here, I put a lot of useful links for anybody that wants to investigate further, but this is basically all the leaderboard of the best embedding models today. And you can see embedding models for different languages or for different subtasks that maybe are more relevant for your task. So you take your text chunk, pass it through the embedding model, get a vector. This vector will have the property that you can do semantic search on it easily. So this is a naive RAG, just copy and paste the relevant information into your context of the LLM. Even on knowledge that the LLM is expected to have, you already see that base model is worse than base model plus RAG. Just do the most naive thing of implementation of this. So maybe make it.
Basic question, because I'm not very familiar with that, but how is it different from just putting all this information in the context?
Good question. In Zoom, everybody heard The question is, why not put the all the information in the context of the LLM instead of doing that? It's a good question. Basically, if you have small amounts of information, it's a good idea to do, maybe to put everything in a context. And for next language models, probably it's going to be increasingly more true what you said, because the context windows are increasing by a lot. But if you have a really big data set or multiple types of data sets, today's LLM, if you just dump everything, they're going to be confused. So it's better sometimes to retrieve the relevant stuff.
It's just a compression or something more than a compression of information? It's
not just compression, it's about performance. Like you will get better performance with RAG than if you put the entire context, because the LLM gets confused.
Like attention behaves differently, better from vector database?
We need to remember that the LLMs didn't learn in the training process of the LLMs. They never seen a context window more than like a few thousands, because it's really expensive to train stuff like that. So current versions will work better with RAG. People like did experiments. But okay, so this is naive RAG. But we'll go into the advanced RAG probably in the workshop, but basically you can do a lot of things that are pre-retrieval and post-retrieval. Like pre-retrieval, you have a lot of things like low-hanging stuff that you can do, like to improve the naive thing. For example, you can index your dataset with overlaps just to increase the accuracy. You want the exact chunk and not just something in the middle. You can do query optimization. You can say, okay, I retrieved the chunk. Now you said LLM, just rephrase all the relevant chunks that I retrieved to make them useful for the LLM. So you use the LLM to improve the context. You can do stuff post-retrieval. You can do re-ranking. Let's say you got 100 relevant results. So you rank them and you deduplicate them. You can use LLM to do it. You can compress them in order not to confuse the LLM that has problems with large context. So this is RAG, where we're going to go more deeply into it. Basically, just to sum up, you want to use RAG when you want to inject large quantities of unique knowledge that doesn't fit in context window. Or you want the LLM to be up to date with updating datasets, like the web. Use it to retrieve search results. This is the level of depth we're going to go into, not more. So the next thing is fine-tuning. So the question was if RAG is relevant for the end user just using the chat interface. I thought that the ability to customize your own GPT, and I thought it's RAG, but it turned up it's not. I was really like, it was disappointed. I thought it was just the obvious thing to do, but what they did actually is something cheaper to implement, which is just summarize everything you uploaded, all the documents you uploaded, and appending that to the context. Yeah, this is a way you could have used, like you could probably create your own. If you have a data set, you can interface with the API, connect to RAG. It's really a nice, easy weekend project. You can do it easily if you have interesting data.
You don't need to code to use RAG. There are like tons of implementations of RAGs all over GitHub. Just pick one.
It's really easy today. A one-liner.
Do we lose some sort of semantic knowledge? I mean, I tried doing that before, but for example, with code, I found that it really compressed things that are really important. So I stopped using it. But
yeah, it depends on the embedding model. Like I have little experience with code, but I will not be surprised if you have an embedding model that is specific for code that will be better. If you use just a generic English, maybe it's suboptimal for that.
So it's good for big chunks of text or whatever, like pieces of knowledge and not.
Yeah. Okay, so fine-tuning is something I'm not going to go in depth because Owen prepared something a really great lecture. So you will get the deep stuff there. But basically what I want to say about fine-tuning is that you use it when you want to change the behavior of the LLM in a way that is, it's not just injecting knowledge, because it's also that, But if you also want to change the style, or you want to do some kind of like a more deep change to the LLM,
I know that people remove censorship like this.
they fine-tune and then
they take mix trail and stuff like that, and then tell it to stop being shy about how to make bombs and stuff like that.
yeah, people are doing stuff like that. But yeah, so nowadays, like fine-tuning is the easiest thing in the world. Like you can do it today very easily in OpenAI. Like you just choose the model you want to fine-tune. You upload your data set, drag and drop. You prepare it in the right format. You just click create, and you have your fine-tuned data. If you want to do it with like open source models like Llama, you can do it also really easily with this library, this torch tune. This guy that is claiming in the clickbait of why fine-tuning is dead. So I clicked, and basically the claim is that when the model is big, the bigger the model, the less reasonable it is to use fine-tuning, because here is an example. What did I do? How do I go back to the F? So this is an example of when you have a small model. When you don't do RAG and not fine-tuning, you get really poor result. When you add RAG, you get increased result. And then when you add also fine-tuning, you get an even increased accuracy in this task. Now, it doesn't matter what it is, but here you see something strange, that when you have just RAG, for the larger model, it's almost identical to doing RAG and fine-tuning. And it's a trend that people observed, that when you have a bigger model, you can just do what's called in-context learning. And RAG is a type of in-context learning. You just put your relevant information and it's better. And actually fine-tuning can cause things that people call catastrophic forgetting. So you can forget stuff, you can inject the knowledge, but you can forget stuff that you learned. For large models, it's probably not the right thing to do. So these two methods are a way of injecting your knowledge into the LLM. So now we switch gear and talk about structured outputs. Good. Okay. So structured outputs, why do we need that? When we interact with the LLMs just for fun, in natural language, we can ask questions and get answers. But when we want to integrate the LLMs into a product, you want the LLMs to be backwards compatible with code. So right now people are doing, like if you want, for example, JSON, what people use before structured outputs is just say, okay, LLM, please give me the JSON and hope that the JSON will be good. Or say some stuff like, if you don't give a correct JSON, I will take a life, or stuff like that. And people actually committed this kind of code to the. So we don't want to do stuff like that. So we invented structured outputs, which is a way to validate and make sure that the outputs of the LLM will adhere to some schemas, JSON or otherwise. So the most basic thing is something like OpenAI JSON mode. So you say you add, when you call ChatGPT, you just say that you want JSON, and OpenAI provide different mode of inference, and also you have different model that was fine-tuned to get better with JSON. So you have a better chance of getting the correct, what you want. But nowadays, I think JSON is not the right way to go for most people. Like if you're already working in Python and you have Pydantic, so instead of doing specifying everything, all the JSON, the complicated JSONs, and doing all this work of putting all the structure of your functions into JSON, what you can do instead is define your structures with Pydantic, which is the library that is doing a lot of work for you, a lot of validations that you get the correct types every time. Like for example, here you can see you can define delivery, which is the base model of Pydantic, and you can define the two attributes, time step and dimensions, and Actually, when you define the object delivery, no matter how, even if the dimensions you entered strings, you will be converted automatically to ints because Pydantic is doing it for all these things for you. So you get all these validations so that your code will be well validated like this. So Pydantic, okay, so Instructor is a library that uses Pydantic to interface with an LLM. So basically what you do is you import Instructor and you define some kind of class, like for example, user, and user has a name and an age. Then you can take, for example, here, like the cloud model. And what you say is that you want the response to be of the type user. And then when you call ChatGPT, this variable, RISP, will actually be of the type user. You can guarantee that. If not, you get some kind of an error. But like Instructor doing everything under the hood for you.
Guaranteed, or does it like fail sometimes?
I will talk about guarantees, but if it's not going to give you user, you get an error. So it's going to at least give you an error, as opposed to just hoping that you will get, for example, with JSON, that you will get all the fields that you want. So you hope here you get an error. But if you get an error, you can do second try, third try. And you get it only after the tries. Like if you don't get it until max tries, you'll get an error. But most of the times, it's going to work. The point is that if you have an error, you will know it. Yeah.
Pydantic and Instructor.
So Instructor is built on. So what's the difference? What's the difference between Pydantic and Instructor? So the difference is that Instructor is built on Pydantic. And an Instructor is a way that uses Pydantic to interact with an LLM. So we talked about validation. So you can use a Pydantic validator, which, as you can see here in this example, let's say you want your name to contain space. So you have defined some kind of a function that checks that. And then when you define your Pydantic model, you can have a validator that checks the name contains space. And if it doesn't, you get an error, which is something you needed to do before, is do some kind of a regex and extract the name and just manually validate. And here you just do it in code, which is nice. You can also do LLM validation, which is a bit more sophisticated than just checking low-level stuff. You can say, okay, you can have a validator, just don't say objectionable things. And when you define the question answer, so what's the meaning of life? It will run under the hood. You send this to the LLM, and the LLM will return the validation. And if the LLM says it's not passing the validation, you'll get an error. So it's just a way of doing everything with code. And instead of writing stuff in text edit, you write it in IDE. This is what Instructor lets you do. You have an option to do retries, max retries. If the first attempt doesn't work, you can append the history and say try again. And also you can do more like fancier stuff that it's hard to do in JSON. So you can define graph structures, nested structures, and everything and the LLMs will give you the structures that you want. So for example, here you can define graph structure with nodes and edges, and you can define this function to visualize them. And then you can ask ChatGPT to give you a knowledge graph of, for example, of physics, and then quantum mechanics, and then you get stuff like that. This is really powerful. Actually, Instructor was so powerful that I just essentially copied the main functionality, and right now they are doing the same thing with Pydantic. Now they have a model that is trained specifically for structured outputs, and they claim that with this parameters tricks equals true, you get 100% adherence to the schema, like the JSON schema or Pydantic functions that you enter. So you probably don't need an Instructor for most things, but Instructor is much more expressive in terms of what you can do. You can do stuff also with vanilla OpenAI. Okay, so this is structured outputs. Yeah, what's the question? The question is if you can make instructor work with LangChain. The answer is yes. It's just open source project. You can integrate it with whatever you want. So until now, we talked about how to inject your knowledge into LLMs, then structured outputs. From now on until the end, we're going to talk about the part of hallucinations, more about the part of multi-step reasoning, like to increase the ability of LLMs to do multi-step reasoning. So I'll show you some video of Magnus Carlsen, the #1 chess player in the world.
Most of the time, I know what to do. I don't have to figure it out. I don't have to sit there, calculate for 45 minutes, know the right move. Usually I can just feel it immediately.
Why do you sit there for a half hour? We've been watching you for a week and you're sitting there until we're watching the paint dry.
Well, because I have to verify my opinion, see that I haven't missed anything. But a lot of the time it's fairly useless because I know what I'm going to do and then I sit there for a long time and I do what
So today's LLMs are basically like Magnus Carlsen, but lazy, that doesn't want to do this verification. So basically what I'm saying is we need error correction strategies to insert error correction strategies to LLMs, to make them more to make them better in specifically multi-step reasoning, but overall being better at giving you the correct answer without hallucinations also. So what I'm going to speak from now on is just how do you invest compute in inference time as opposed to the training time to make the model better. How do you get your fixed model and in inference you call it multiple times in sophisticated ways in order to get a better result than what you could have gotten if you just asked the model in the chat. Actually, this is a point that will be relevant, that inference is probably going to be more important than training in the long term, because maybe the training will get to some kind of a plateau, but people will, in order to increase the level and reliability of the models, will just invest more in inference. And this company, Grok with the Q, it's actually cool what they're doing. They have this chip that called language processing unit. They get crazy speeds in LLMs. It's not even close to everything else, and also fairly cheap. If inference is indeed more important, they might be a competitor to NVIDIA. Right now, they raised a lot of money. Let's see. But the first way to invest in inference compute will be tree search. So skipping the chess thing, the way you play chess with computer today, the state of the art things is when you have some kind of a model like in the LLM that will look at a position and tell you, is it good for white, is it good for black? But if you just use that, it's going to be good, but it's not going to be the best chess entity in existence. But what people are doing is they're doing what's called a tree search. So what they're doing is they do look ahead for future positions. They sample the best potential moves for the next, and then they see where am I after one step, and then they evaluate that, and then they say, okay, what's the possible moves here? And they just make this tree and evaluate the options, all these leaves. For each leaf, you say, okay, in this leaf, is it better for white or black? And then you aggregate everything until you say, okay, this path in the tree is the best, so let's go for that. Like people probably do look in their heads for something like hundreds of moves, but maybe probably less. The old school, like Deep Blue type of chess engines look at it's 10 million moves per second. They verify, like they check how good they are. And like recently, the approach that one was to do less search than that, but still a lot more than humans. So it's a combination of intuition and search. So people now are trying to do the same thing with LLMs. If you have a task that can be reasonably broken down into a tree search, then you can get really big gains when you do that. So the idea is called tree of thought. It's like chain of thought, but a tree. Everybody should know chain of thought, but I'm going to go over it again. So you have just I/O prompting, which is just input output, just you prompt. Then you have the chain of thought. You say LLM, just think step by step, and you get this. So this is the chain of thought. Self-consistency with chain of thought is you have chain of thought, but you do a lot of them, and you do a majority vote on the outputs, and you take the majority answer. This is better than that. This is better than that. Tree of thought is at each step of the chain of thought, you actually evaluate the individual step. And then you go ahead with the most promising steps. We'll see an example. Okay, so there is this game of 24, which many know. You get 4 numbers, and you need to get to the number 24 with the basic arithmetic operations. Do you want to try with these 4 numbers? Get to 24. Say it. 15 plus 9. 3 times 5 is 15. Plus 5, yeah, okay. So this is another solution. You can have more than one solution. Good. So this is a game that the LLMs are suck at. They don't know how to do. Single-digit accuracy. Strange, right? It's easy. But okay, so let's see what's tree of thought applied to the game of 24. So what you do is you say to the LLM, okay, propose the next move. So you get the 4 numbers, propose the next move. And then the next possible moves that you can have. And then you also have a validation prompt. So you ask the LLM, evaluate to say if you think is impossible to get from this step to 24, likely, or are you sure that you can? So this is the evaluation. And what you do is you get all the options, you evaluate all of them, and you keep going just with the promising ones. And when you do that, you get 70.3% accuracy in the game. Chain of thought, for some reason, gets you worst result. Self-consistency gets you 9. But tree of thought with B is the breadth of the tree. So with B equals 1, you get 45%, but with 5, you get 74%, which is crazy that you can do such an improvement. And if you do 100 chain of thoughts, and you don't do the majority vote like the self-consistency, you take the best one, like, as if you're an oracle. Still, you get only to 50%. So it means that with 100 chain of thoughts, you will get, on average, just 1 correct result, which is, it's impossible to know that it's the correct result if you don't have the oracle. So this is extremely powerful if it's applied to the correct domain. So the question is, how do you evaluate? It's like when you evaluate a move in chess. You don't really know if this is a good for you or bad for you, but you have a guess, and then you go to the next position, and then you evaluate there. So the idea is what I wrote here is, so you look ahead to states where discrimination, like saying what's good or not, is easier than generation. Like, for example, in chess, going to the checkmate position, it's easy. You know it's checkmate. You don't need to be a grandmaster. You want to do it like before, like in the beginning of the game. So this is the challenge. So that's the reason you need to decompose the problem into steps and evaluate each step. More questions? How much time do I have? Okay, it's enough. So the next way to invest computation in inference is called program search. Is basically when you have a domain like code or something similar, that you have a verifier that is like a compiler, that you can just run the code and you can know what's the result. You can do some kind of a brute force sampling of the LLM. And then because you have the compiler, you can just sample from the LLM and then run the code. and see which pieces of code will give you the correct result on your example. For example, here, this is alpha code. This is from DeepMind. What they did, they have this data set of problems and solutions in code that are, again, these are problems that without like vanilla LLMs will get close to 0% correct. So for each question, you will have an example solutions. So you can have 1 or 2 or stuff like that. But then you need to be correct on a test set. So what they did basically is that you ask the LLM, just give me many examples of this solution that you think is the solution for this problem in the thousands. And then you do some kind of filtering and clustering. You see which ones ran, which one didn't, which gave the correct result. And you take just the most promising results. So it's basically brute force, just sample and see what's working. And this stupid method will get you very far, actually. If you have a budget, computational budget, you can get to really, really good accuracy, like on par with humans on this kind of questions. The bigger the model, the better it is scaling with the number of samples that you sample, which makes sense. Because when you have a bigger model, probability that one of the samples that you will sample will be correct is higher. So if you sample more, you will get correct. Eventually, you get something correct.
Look, it looks like a product manager's dream. It's like thousands of monkeys were faster and better.
Right now, it's probably more expensive than developers. Yeah. But this is just 41 billion parameters models. Like imagine that today's models, like Claude 3.5 Sonnet, with this, probably you get very far.
How much we have right now? What is the sizes of the Sonnet? And
we can ask, what's the sizes of Claude 3.5 Sonnet? I don't know. I don't think they published this. But probably in the order of trillion parameters. This is GPT-4, I think. But I don't know. Like it's in the order of trillion, probably.
I think what's a bit nice here is that even 9 billion model, which is something you can run on a personal computer, is almost as good as 41 billion model.
You have models that are 70 billion that you can run with the 70B.
Even 7B can.
Can if you decrease the precision by a lot. But you can imagine like coding.
But you will need to run the compiler like thousands of times.
Yeah. But if you have imagine that you have a really like you have an important task, you can just run it. If you don't care about money, you can run it. Yes.
finding 0-day exploits like this.
Yeah, probably people are doing it now. So this is a program search, but the same approach were used. There is this challenge that's called ArcAGI, which is some kind of intelligence test type of questions that you have some kind of geometric transformation and you need to fill in the unanswered part. So what this person did is basically the same, but he converted this kind of data to code, which is easy because it's just grid of stuff. And then when you have, and so you have two examples of the, and you need to infer the third. So what it is, just created a lot of programs. Here you can see that when you sample more, you get better accuracy. So the same thing, and just nobody if you just do a naive prompt, you get close to 0% on this task. Which is surprising because this is also seems like an easy thing to do for a human. Maybe you can find hard examples, but this is not a hard example. This is easy. I think we'll see more of that, probably, like sampling a lot. And it's convenient to do when you're in the domain of code. Because code, you have a verifier. It's harder to do today is when to use the LLM as a verifier for itself, which is actually the thing that we did when we did the tree of thought. The LLM is a verifier for itself. Like if each step of the way you ask the LLM asks itself, this is reasonable or not? And for that, LLMs are still not at the level that they need to be in order to be useful generally, like broadly. Okay, so with that, let's go for the last thing. We'll also have a workshop on that. Agents, which is a loaded term. So my ugly definition will be neurosymbolic generation verification loops, which is kind of things that we talked about in tree search and program search, like verification or neurosymbolic. What's neurosymbolic? Symbolic is the compiler is the symbolic part, and the LLM is the neural part. So okay, so agents basically it's LLMs with agency. Just part of when people say agents, almost every time they mean that you allocate tasks to external tools and other specialized models, and then you close the loop with external or internal verifiers. External verifier is the code interpreter. Internal verifier is like the LLM itself, probably, or other LLMs can be. And you have a lot of tools to build such things. Really convenient, high-level languages, like that you can just with very few lines of code have a team of agents running and doing stuff for you. And we have a workshop building stuff with I'm not sure which framework we'll build, but probably LangChain. If I know, it's probably going to be LangChain, but it doesn't matter really. And this is a quote just for the future that I think is revealing. This is from Dario Amodei, is Anthropic CEO, one of the most important people in AI today. And he said,
if you want an agent to act in the world, usually that acting requires you to engage in a series of actions, right? You talk to a chatbot, it only answers, and maybe there's a little follow-up. But with agents, you might need to take a bunch of actions, see what happens in the world or with a human, and then take more actions. And so you need to do a long sequence of things. And for that long sequence of things to actually work, the error rate on each of the individual things has to be pretty low, right? If I'm a robot and I'm like, okay, I'm going to pick up this thing and walk over there, and then I'm going to pick up that, I'm building a house or something. There's probably thousands of actions that go into that. And so all of this is to say the models need to get more reliable because the individual steps need to have very low error rates. And I think part of that will come from scale. Like we need another generation or two of scale before the agents will really work.
We talked about that, but I think coming from this guy is probably has some kind of internal information of the next generation models. So it's exciting times in this agent things. So we have just to let you know about this. The benchmark that everybody is benching themselves upon is the SWE bench. It's basically it's real world GitHub issues. Like you have a repo and you have a bug, and to fix the bug you need to change more than one file, more than one function, more than one class. It's complicated. Just GPT-4 by itself will get you not very far. Probably like a 3% level. And people are making big strides on this. Like recently, people got to 45%. If you can debug, it's a lot of our work going to the machines. The code runs with the correct tests. Yeah. Okay, so just a reminder, these are the upcoming lectures that will go into more depth about RAG, agents, fine-tuning. Come and learn something. No, we don't have time.
לגבי האפטר וייב, להשתמש ב-out of the box, כאילו הדקורטורים של פייגנטיק, יש להם כזה, ומה זה שונה? כי אנחנו משתמשים בדקורט, כאילו בפינקוד. חשבתי שזה כאילו...
זה רק דרך אחרת האמת שיכול, אם יש הבדל אני לא מכיר.
הבנתי. וה-LLM validator זה כן בשילוב עם האינסטרקטור. כאילו זה, כן, גם בזה אנחנו משתמשים